Alright, so I'm going to go ahead and begin to go over section 5.4. We're going to look at some basic integration formulas, and then we're going to look at what we call the net change theorem. Alright, so to begin with this handout, what I have is a whole bunch of integral formulas, and you want to try to get down to a point where you can memorize all these things. A lot of these things you really already know, though, because you know derivative rules. So that's kind of what we have on this first page here. So if you look over this, you know, for instance, we know that the derivative of e to the x is e to the x, so these things match. Okay, we also know the derivative of ln of x is 1 over x. Therefore, the integral of 1 over x is ln of x, and so forth. Okay, there's the power rule for a derivative, the power rule for an integral, and so forth, right? So a lot of these things you're going to find that you know. These are all anti-derivatives right here, so if you know your derivative rules, then it goes backwards. Here's one more example. We know the derivative of the tangent is the secant squared. Therefore, the integral, or the antiderivative of secant squared, would just be equal to the tangent. Okay? So that's what this is trying to show. All of these formulas right here are backwards, reverse of the derivative formulas you already know. Okay? And these things are all pretty important. I think if you're going to go on to Calc 2, a lot of things show up. These particularly show up a lot, actually, in Calc 2, like this inverse sine, inverse cosine, inverse tangent. So it's important you try to memorize as many of those as you can. Okay, next page we're going to look at basically some rules that we've already talked about a little bit. So these are the basic properties of an indefinite integral. I'm going to give you a few examples of each one now. So this first one is just the constant rule. You can take out a constant multiple. So for instance, if you had something like 3e to the x of dx, well, you know that you can take out that 3, and then you would have 3 multiplied by the integral of e to the x dx. That works the same way that limits work and the same way that derivatives work. Okay, so it's kind of derived from that idea of a limit anyway, so it works the same way. Of course, then the answer to this would be 3. We know the antiderivative of e to the x is e to the x, and then plus c. Okay. Next two rules really go together. This is just kind of sum and difference. I'll kind of put both of these together and just give you one example of this. So let's say that you had something like the integral of 1 over x, and then let's say we had something like x squared, and then let's say we have subtract. We have something like the cosine of x times dx, like that. Well, what this rule really says that you can do, and again, it comes from the idea that we can do this on a limit. We can break limits up into sums and differences. So what we can do is we just do 1 over x dx plus the integral of x squared dx, and then minus the integral of cosine x dx. Then we can perform those antiderivatives. Again, you're going backwards. What do you take a derivative of that gives 1 over x? That would be ln absolute value of x. Okay, this one is a power rule for integrals, so remember what you do is add 1 to the exponent. Exponent goes up 1, then you divide by the result. And that's totally backwards of the power rule for a derivative. In a derivative, you subtract 1 from the exponent, and then you multiply by that exponent. Okay, really, you bring the exponent down, subtract 1. So this is just doing this in reverse. Okay, and then we know that the derivative of the sine of x is the cosine of x, so that would be the answer to that integral. So those are real important rules that you utilize quite a bit. Okay, the next set of rules. Okay, so with this next set of rules are real important to know, and they all kind of work the same way. This is just when you have a constant involved within the function, not a constant outside the function multiplied where you can bring the constant out. It's embedded in this. So this is almost like kind of a chain rule for integrals in a sense. So the idea on this is, and they all kind of have this same structure here, the idea, and I'll just go through this first example right here. For instance, you know that if you have the derivative of the sine of 3x, well, no, you can't bring the 3 out, obviously. I hope that's obvious to you anyway. So what you do is the chain rule, you do cosine of 3x times the derivative of 3x, which gives you that. So you end up getting 3 cosine of 3x, okay? Well, what this is dealing with is what happens if we have the integral of the cosine of 3x, okay? Well, it turns out what you do there is you do 1 over this. So think about the chain rule. You multiply by the derivative of the inside part. Well, here what you're doing is you're dividing by the derivative of that inside part, really. So you're doing 1 over 3, like that. And then we know the antiderivative of the cosine would be the sine of 3x, okay, plus c. So that's how that works. If you look through the list of these formulas, you're going to see that over and over again. Now, keep in mind that you always have the ability to check your answer. So let's just check and verify that this works on this example. So if we were doing the derivative of this, 1/3 is a constant. So the constant really comes out of the differentiation. The derivative of sine x is cosine 3x, but by the chain rule, we multiply by the derivative of the part inside, like that, and of course the derivative of the constant is 0. So what happens is you have the 3's crossing out, so you have cosine of 3x. So that's basically how that works out. You're going to divide by that number a, and if you look at all these examples, they're essentially saying the same thing. If I do the integral of the sine, we know the integral of the sine is negative cosine, but in this case it's negative 1 over a cosine of ax. Okay? We know the antiderivative of secant squared is tangent, but if there's an ax there, it just becomes 1 over a tan ax plus c and so forth. So these things are just adding in that constant multiplied inside the function. Now that's got to be a constant. It can't be like a variable or something. You know, we're just talking about some constant in there. So that's how that works. And these are real important to know because they pop up a lot. And if you don't know how this works, then you're forced to use what we call U substitution. And you want to be able to do these without having to bother with U substitution. Down at the remaining list of these things basically works the same way. Okay, so this next list of integrals essentially just saying the same thing. If you have integral of e to the ax, it's 1 over a e to the ax plus c and so forth. Okay, like that. So let's see, that's basically it, I think. Let's see, I think all this stuff right here, these show up quite a bit here too. These inverse trig functions show up quite a bit here the same way. So you can kind of look at how these work. These things work, particularly this number 10, works like this. So if you were doing the integral of dx, and again that a is some sort of a constant, so if that was 4 minus x squared, this is something you'll see quite a bit. What this is this is really 2 to the second. So a is 2. So if you follow this formula, that would be the inverse sine of x over 2 plus c. So you want to look at that. See, these work a little bit different on this, and the tangent one works like this. I'm going to go through an example of this tangent one because this does show up a lot, particularly in Calc 2. So say you had 16 plus x squared. Well, that's 4 squared, so a is 4. So if you follow this formula, it goes 1/4 inverse tangent x over 4 plus c. Okay, so that's how that works out. So those things right there work a little bit differently on the inverse trig functions. And then there's, don't forget that you also have one for a cosine and the other, all 6 of the trig functions, okay? All right, so those are pretty important to know and to understand how they work. Now we're going to go on the next page, and then we'll start working out a few things here. Okay, now we'll go ahead and work out some indefinite integrals here. To begin with, this one we're going to be doing the power rule. So in utilizing integral theorems on this, or rules, the thing that you would want to do is you would want to split this up. All right, so let's see, we have cube root of x dx, and then minus 1 over the square root of x dx. So we're going to split that up into 2 integrals. And what we need to do is rewrite these as rational exponents so we can use the power rule for an integral. So we're going to write this as x to the 1/3 times dx. Okay, this right here, this is really 1 over x to the 1/2, but you need to bring that to the top to make that x to the negative 1/2 dx like that. Now we're set up so that we can go through and integrate by the power rule. Okay, so the power rule goes like this. It's kind of can be thought of as the opposite of the power rule for a derivative. Instead of subtracting 1, you add 1. So I'm going to add 3/3. That way I've got a common denominator. I divide by the result, which is 4/3. Move to the next one. I do exactly the same thing. I need to make the exponent go up 1. I divide by the result, 1/2, and then I've got my arbitrary constant c. Okay, now what I need to do from here, a couple of things, you'll do this quite a bit. Whenever you divide by a fraction, you know that you're multiplying by the reciprocal. Okay, so you could write this as 3/4 x to the 4/3, and it's okay to just leave it in that form, minus 2 over 1, so it would be 2x to the 1/2 plus c. Okay, so that would be the antiderivative. You could check that easily by doing the derivative. If you did the derivative of your answer, you could eventually work your way back to the beginning of the problem. Okay, so the next problem, we're going to basically do the same thing. We're going to break it up into 2 integrals, e to the 4t dt minus, and then you can go ahead and bring that half out. You can skip this step if you want to. But just to start with, I'm going to go ahead and break it up into 2 integrals like that. Then you can take out the constant. You can, skip some of these steps. So this is e to the 4t dt minus 1/2 times the integral. And I'm going to write this as 1, not like that. Okay, like this. I'm going to write this as e to the 1/4 t times dt. Okay. Now, we have this integral rule, and this is where you get into this AT form. So let me just kind of refer to this on the previous page. And again, I was saying I think it's real important that you try to memorize as many of these things as you can and really get solid with this. So what we're really utilizing is this integral form right here. So we're going to have 1 over a e to the ax. Okay, so when we get the antiderivative here, okay, you can think of this as itself times 1/4. Okay, and then over here we would have 1/2. The antiderivative here would be 1 over a, so see now it's 1 over a 4th, and then e to the 1/4 t plus c. Now all we need to do is clean it up. So notice this part right here. If you just look at this piece right here, this is the arithmetic. You would handle this like this. Okay, really 1 divided by 1/4 is 1 times 4, so that's 4. So you would end up having 1/2 times 4. Okay, so we have 1/4 e to the 4t minus 1/2 times 4 e to the 1/4 t plus c. Okay, and then 4 over 2 is 2. So the final antiderivative could be written as 1/4 times e to the 4t minus 2 times e to the 1/4t. Now you could change that back to t over 4 if you wanted to. And then that would be an acceptable antiderivative of that function. Again, that could be checked real easily by doing the derivative of your answer. Okay, and I always recommend when you're learning integrals, you're doing your homework, try to check your answers as you go through these things. Okay, all right, so that'll wrap up that idea. Okay, the next thing I want to look at is this next integral. Sometimes students don't recognize this. If you have an x in the bottom, you know, we know that the derivative of ln x is 1 over x. Okay, so we know that. So the thought on this is I see that x there, it's kind of making me think that. Well, you can also think of this as a 1/3. So what you could do here, the best thing to do here is just pull out that 1/3. So you'd have 1/3 times the integral of, and then I would write this as 1 over x dx so that you clearly see that antiderivative. Okay, so we know that if you take the derivative of ln x, you get 1 over x, so this would be 1/3 ln, and when you do this integral of 1 over x, it's not acceptable to just say ln of x, you got to say ln of absolute value of x plus c, and the reason for that is remember, a log, you can only take a log of a positive number. The logarithm of 0 is undefined. The log of a negative is undefined. So that's why you need that absolute value to guarantee that x is a positive number when you do the log of it. Okay, the next one represents something that you have to do algebraically. You have to work with this one a little bit algebraically first. The best way to do this one is to split the fraction up into two parts. So we're going to say x squared over x minus 1 over x times dx, like that. We can simplify, that is x squared over x is x. Okay, and then we'll split this up into two integrals. Now you can do this in your head. It's easy to get the answer to this problem in your head. Partially what I'm going through in this section is showing you how these integration rules work. So I'm going to go ahead and just split these things up into integrals like that. Now you're ready to get your antiderivative. So you're going to do a power rule here. Add 1 to the exponent. That would be x squared over 2. Again, the antiderivative of 1 over x, like we just saw, is ln absolute value of x plus c. Okay, so that is a good antiderivative there. A lot of times you can write this if you want to. You don't have to, but you could write it as 1/2 x squared minus ln absolute value of x plus c also. Okay? Okay, so what I'll go ahead and do now is I'm going to go ahead and pause my video and give you a chance to work out the next 4 problems. So I want you to do the problems on the bottom of this page and then move on to the next page and work out those integrals as well. And then we'll come back and we'll check our answers. Okay, time to check our answers and see if we got these right. Okay, so the first one you can look over here, just go ahead and check your answers. I'll kind of talk through some of the details of these things as we go. All right, so this one you should have got 20/3 x to the 3/4, subtract 21/5 x to the 5/3 plus c. And I'm just going to talk through what I did. The first thing is you change to rational exponents. You wanted to bring this to the top so that it's 5x to the negative 4. Third step, I'm removing constants. You know, and a lot of this stuff you can do in one step. You can just kind of get all this set up in your head mostly. And then right here is where I'm actually doing the antiderivative. So notice I'm adding 1 to the exponent, dividing by the result. Over here, add 1 to the exponent, divide by the result. So again, you'll get to a point where you can save steps, because if you're dividing by 3/4, it's just multiplying by the reciprocal. When I do the problem, I don't usually write this step out. I just know dividing by the fraction is multiplying by reciprocal, so I jump to this step here. Same thing here, if the 5/3 is multiplied by 3/5, then I multiply straight across to get the 20/3 and the 21/5, like that. So that is your antiderivative. Okay, this one, Again, I split it up into two integrals, subtracting the two integrals, just bringing that down. Take out the constant of 1/10. I'm going to write z over 2 as 1/2 z. It's a little bit easier to interpret that way, I think. Then we have this. And then the integral rule that we looked at is if you have the integral of e to the ax dx, that's 1 over a e to the ax plus c. So that's what I'm doing there. I'm doing 1 over that number in front. See, each time, that's what I'm doing. So I'm just basically applying that integral rule. So I have 1/10 times 1 over a half e to the 1/2 z minus 1/3 e to the 3z plus c. Okay, and then again, this is 1 divided by a half is the same as multiplying by 2 over 1. 2/10 becomes a fifth, and that's it. Okay, all right, so that's the answer problem. Let's move to the next page. Take a look at what we have here. Okay, this one, there's really two rules you're looking at. You're looking at the integral of cosine x dx is sine x, and then you're looking at the integral of the sine x dx is equal to negative cosine x plus c. Okay, so that's what we're doing. So I split it up into two integrals, brought my constants out, and then applying the rules. The integral of cosine is sine x. The integral of sine x is negative cosine x. Work out the details. You should have got 2x plus 4x, or 4 cosine x, and then plus c. Okay, and then the next stage kind of works like this. I'm really looking at two integral rules. If you're doing the integral of secant ax tangent ax dx, and you can go back earlier in your notes and find these formulas, but the way I remember this is I know the derivative of a secant of x is a secant x tangent x. Okay, if you know that derivative rule, then you're just simply working in reverse. Then you have that ax thing, so you go 1 over a, and then it just becomes secant of ax. The other thing you're doing is the integral rule for secant squared of ax. Okay, and the way I look at this is I look at, well, the derivative of a tangent of x is a secant squared x. Okay, so the answer to this integral is going to be then 1 over a tangent of ax plus c. Okay, so that's how that goes. I'm trying to just show you, if I know my derivative rules, then I can reason out the integral rules pretty well. So you can see what I did here. I broke it up into two things, and then I'm just using these rules. The integral of secant 2x, tangent 2x is 1/2 secant 2x, applying this rule. The integral of secant squared of 9x is 1/9 tangent 9x. That's how you get the answer. Okay. All right, so that's going to be into part one of the video. I'm going to do the net change theorem in a second part. A little easier sometimes, make the videos a little shorter. All right, hope this helps you to get started on working out integrals.